Welcome back to my YouTube channel. Today we're going to talk about two separate but related organic chemistry reactions. We're going to talk about the Claisen condensation first, and then we're going to talk about the acetoacetic ester synthesis second. The way I want to structure this video is I want to talk to you about kind of like the general ideas of it on this page. Then I want to introduce you to some of the reagents, the intermediates, and the products involved in all these reactions before I talk about the reactions themselves, just so you have a better idea of what it is that's going on. And then lastly, I want to talk about each one of these reactions, the Claisen condensation, the acetoacetic ester synthesis, in detail regarding what the general mechanism for each of them is, and then what the specific reaction mechanism for each of them is. First, I want to talk to you about the sort of general idea of this. The idea is that these are two separate reactions, but they're related in the sense that the product of the first reaction is going to act as a reagent in the second reaction. And the idea is that in the first reaction, we're going to take two esters, we're going to convert them to a beta keto ester by introducing an alkyl halide, as well as a few other reagents involved to make this work, which is kind of to produce a beta keto ester, which is kind of like just an ester with a ketone, exactly 2 carbons away from the ester of the carbonyl of the ester group. And then we're going to take this beta keto ester, and we're kind of going to get rid of the ester portion, and while also introducing 1 or 2 R groups to it, producing either a mono or a di-substituted acetone. So that's the general idea of it. Let's talk about some of the key players involved. So here, the way I kind of organized this little page is that these 2 rows right here are either reagents or intermediates, and then this row is the products. Again, like I said, there's only really 2 products, or there's 1 product for each reaction totaling for 2, which is why you see only 2 products on this little column, and here you have some others. Let's talk about it starting from the order from going here, 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 and here, here. So let's talk about this first one. So this first one, by the first one I mean this. What you'll notice is that this point right here represents a carbon. The carbon is double bonded to this oxygen, and this carbon is also bonded to 2 R groups, which either could be the same thing or they could be different. The idea is that this is called a ketone, and these R groups have to represent some sort of an alkyl group, which means that the R groups represents a sort of carbon with hydrogens attached to it, which could be bonded to other carbons, or it could be bonded to something else, or it could just be a carbon and solely hydrogens, in which case you get an acetone. If we have, for example, a ketone, but instead of having 2 R groups, we only have 1 and the other one's a hydrogen, you would call this an aldehyde. We're actually not going to talk about aldehyde at all in either of these reactions. I just wanted to introduce this idea to you to say that this is what you get if you have a hydrogen in place of one of the R groups of the ketone. And then lastly, if both of these R groups of the ketone represent just a methyl group on either side, what you get is called an acetone, and that's what this is. Here you can see this is a carbonyl group, the carbon double bond to the oxygen, and then each of these R groups is just a methyl group. It's just a carbon with 3 hydrogens on either side, and that's what you get. That's what you would call an acetone. It's also going to play a role in these reactions, which is why I talk about it. And then on this second row here, we have something called an ester. The ester is it's similar to the ketone in some ways and similar to not others. So right here, you see this is a carbonyl portion. This is a carbon bonded, double bond to the oxygen, and then it has an R group of some sort, an alkyl group, to either side of it. And then on the other side of that R group, what you're going to find is an oxygen an oxygen bonded to another R group, and it has to be this way such that the oxygen has to be bonded to something else, otherwise it's not an ester, it's something else. You'd call it something else. And so to the right of it, this is just an example of what a possible ester could be and what the possible R groups on either side of the carbonyl portion of the ester could represent. So this is called a ethyl ester. The reason why we call it, and both of these things are the same thing, it's just they're written in 2 different ways. The reason why it's called an ethyl ester is because the R group portion that's attached to this oxygen of the ester is ethyl, meaning it's just 2 little alkyl groups. So this is a carbon here, this is a carbon here. This carbon has 3 hydrogens on the end of it, the terminal carbon, and then this internal carbon right here, that's part of the ethyl group attached to the ester, has 2 hydrogens. And so again, these 2 really do just mean the same thing. They're just written differently. So this ethyl, this ET, which is what ethyl means, represents this, an ethyl group, which is just 2 little carbons with their hydrogens attached to this oxygen. And then lastly, I also got to mention that ethyl ester, this particular ethyl ester has this R group represents just the methyl group on the other side. And so lastly, let's talk about the products. This is going to be the product of the first reaction, the Claisen condensation reaction. This is called a beta keto ester. From the name, you can kind of tell what it means, in the sense that the name kind of gives you clues to what it means. Beta keto ester, so you have to imagine that this is this left part where I've drawn it. This left part is the ester portion. As you can tell, it's an ester portion because here, like I said before, here's your carbonyl of the ester, and then here's the oxygen bonded to the carbonyl, which is also bonded to something else, which is an ethyl group, which is what we have here. And then the reason why we call it a beta keto ester is because this is the ester. This is an alpha carbon or alpha hydrogen, this first one here that's bonded to the ester. And this is the second one, you call it a beta carbon, a beta hydrogen. And the reason why it's called a beta keto ester is because the keto part is beta, or it's 2 units away from the carbonyl of the ester portion. So it's just a way of describing how these are sort of structured, how they're, like, where it's placed in relation to one another. And then lastly, this is the product of the second reaction, what's going to come after this one. This is going to be the product, this product of the first reaction is going to be a reagent in the second one, and then the second one, the product of the second one, is going to be this right here, which is simply a substituted acetone. And like I said before, you can have either a mono or di-substituted acetone, meaning you can either have one arc group attached to it or 2. And the reason why I put or here is just to represent this fact. So here, as you can see, this is the acetone. This is this, but plus an R group here, or if you have 2, it's di-substituted. So yeah. Let's talk first about Claisen condensation. So the idea of Claisen condensation is you don't necessarily have to have, so ignore this top part and focus on this bottom part. I kind of wrote it backwards. Usually I write the generic formula first and then the reaction mechanism second. Kind of did it backwards here. So just ignore this, focus on this. So the idea of it is we're going to have 2, and this doesn't have to be specifically this reagent. In other words, we don't have to specifically have 2 ethyl esters. You can have, if you have a cross Claisen condensation reaction, you'll have 2 reagents that are not identical, and this could be either 2 different esters, or it could be an ester and a ketone. And one of the ideas of it is that, say you have, if in a cross Claisen condensation reaction, say if you have those 2 different ones, you could label one A, the other B, and then the possible products would be AA, BB, A, or AB. Yeah. The idea is we're going to take, generically, we're going to take 2 ethyl esters, and we're going to react it with a base, specifically this base. If you react it with another base, it will go differently. And then after we react it with base, we're going to react it with acid to produce the beta keto ester, which is what I talked about a few moments ago. So let's talk about the specific reaction mechanism. It's fairly simple. So if you look right here, this is what we're starting off with, the ethyl ester right here. You'll notice the difference between this one and this one is that this one I've drawn in hydrogen here. The hydrogen, there's actually 3 hydrogens present on this terminal carbon right here. I just haven't explicitly written them. You just kind of have to assume that it's implicitly assumed that the hydrogens are present, and here I explicitly written here. That's why you see hydrogen here and not the hydrogen here. And then when you use the base, specifically sodium ethyl epoxide, which when you dissolve in solution, the sodium, it will split into positively charged sodium ions and negatively charged ethyl oxide ions. And the idea is that this base is going to remove a hydrogen of specifically the methyl portion of the ethyl ester. So on this side, nowhere else. It's going to remove the hydrogen here, and this is reversible. And then once you remove the hydrogen, you're going to have a negative charge on that carbon. This is also stabilized by resonance, but we're not going to draw that right now. And the idea is, secondly, we're going to, like I said before in this generic reaction, the generic formula right here, you have 2 of them. And this is where the second one comes into play. That is, once we deprotonate the carbon of the ethyl ester, there's going to produce a negatively charged carbon here. Again, you can think about this in terms of resonance structure, so this negative charge is delocalized, but we're going to think about this specific resonance structure. And the idea is that this second ethyl ester is going to come into play at this specific part. That is, the negatively charged portion of this carbon is going to add to the partially positive carbon of the other ethyl ester, and it's going to break the pi bond to the oxygen so that it can form this negatively charged oxygen, and it's going to form a tetrahedral intermediate over here, such that you see that, and I drew this in blue and pinkish so that you can see how these add to each other. And then, so like I said, it's going to form this tetrahedral structure. It's tetrahedral because you see this carbon is attached to these 4 things. And what's going to happen is that the ethyl oxygen is going to be a good leaving group in this scenario, which is why the it's going to be expelled, and in doing so, we'll reform the double bond here with the oxygen, thereby producing the thereby producing kind of in a way the product of the entire reaction, the beta keto ester. The problem is that this base is still present in reaction, and so the problem is that this base is probably going to, and again, these are all equilibrium going reverse and forwards and backwards. In this case though, the product is going to be favored, where that even though we have our product of the reaction, the base that's still left over is going to deprotonate the alpha hydrogen between these 2 carbonyl groups. And this alpha hydrogen here is extremely acidic because it's between these 2 electronegative oxygens, and the electron density is going towards them away from the hydrogen, making it easily acidic, easily broken off. And so that's the problem. The problem is that you can get the product after already doing these 3 steps, but the base is still going to be left over and still going to deprotonate. And so once it's deprotonate, the way that you kind of fix that problem and get back to your product that you want, which is a neutrally charged compound, not a negatively charged one, the way you kind of solve that problem is that you're going to add acid to the solution, and the acid is going to kind of just overcome this and protonate back this alpha carbon, so that is now neutral. And so again, the idea of the Claisen condensation, which is what this page is we took 2 esters, which could either be exactly the same, or they could be different, or you could take an ester or a ketone, and you just react it with base, and they add to each other, and then there is a leaving group that's expelled, and then the base is still left over, so it deprotonates it, and then you can reprotonate the alpha carbon by adding acid, and then you get your product back again that you wanted in the first place, which is a beta keto ester. So next, let's talk about acetoacetic ester synthesis. So again, what did I draw here? Okay, so this is the general formula. I wrote these 2 general formulas. There's a lot of steps involved, but the reason why I wrote, and this is acetone right here, I don't know why I drew that there, ignore that. The reason why I drew these 2 general formula as opposed to 1 singular general formula of the acetoacetic ester synthesis is that you can actually either add 1 R group to your little product, or you can add 2. And so that's why I drew these 2 generic formulas, to show that the top one, as you can see, there's only 1 R group, and the bottom one has 2, which is indicated by the fact that they're color-coded. This one's orange, this one's pinkish. And so basically the big difference between how you get 2 instead of 1 is that after you go through the normal steps of what you would normally do for 1, you simply kind of repeat it again, if that makes sense. So again, this is your beta keto ester. You do all these steps. We're going to deprotonate. We're going to add an alkyl halide. The R represents the alkyl component, and the X represents a halogen of some sort. Then we're going to protonate it, and then we're going to heat it, the reaction mixture, so that you can have decarboxylation, so you lose a carboxylic acid, and then you're going to get your product. And then again, the difference between these 2, why you can get 1 as opposed to 2, is we're just kind of repeat the steps. We're going to deprotonate again. In the second scenario, where we get 2 R groups, so it's disubstituted, to get the second one, you just deprotonate it again using base, and then you add another R group, and then you kind of just continue like normal. So that's a general formula, by the way. Now we're going to talk about, and this is the last sheet, by the way. Now we're going to talk about the specific reaction mechanism. Now, if you notice, like I did in the previous sheet, the first one was monosubstituted acetone, and the second one was disubstituted. I did the same thing here. So this is the first example. This is monosubstituted acetone, which is your product. And this is the second example, which is disubstituted acetone as your product. I'm going to talk about this one first, and then the second one. So here, we have the beta keto ester, again, the product of the first reaction. And as you can see, like I said before, this alpha carbon and its alpha hydrogen, the alpha hydrogen is extremely acidic, again, because of the electronegative nature of the oxygens in between it, which are pulling electron density away from it, so it wants to leave. What you're going to do first is you're going to react with specifically this kind of base. If you react it with another kind of base, it kind of gives works differently. You don't want to do that. So we're going to react with this base, and what's going to happen is there's going to be when you're acting with this base, you're going to deprotonate specifically this hydrogen. And again, the reason why it says hydrogen is because it's extremely acidic as compared to the other hydrogens possible in the molecule. And then what's going to happen is now that there is a negative charge on this carbon right here, or even though you could say that there's resonance structures, we're going to focus on this specific resonance structure at hand. You're going to introduce an alkyl halide, or in this case, this is the only one you're going to introduce. In this case, you can introduce two. And what's going to happen is that you're just going to add the alkyl halide, breaking off the halide portion to the negative portion of this beta keto ester, which was now negatively charged. And then by adding the R group, it's now positively charged. And the idea is we want to get rid of these portions on the left, this oxygen and the ethyl oxygen, so like the ester portion, I guess. And the way we do this is we kind of want to set it up for decarboxylation so that we add, where we're going to heat it so that it loses the carboxylic acid, but first we have to convert it to this ester, this ethyl ester, to a carboxylic acid. And the way we do that is we're going to protonate it first with acid, and then it's going to convert to the carboxylic acid here. And now that it is carboxylic acid, you can heat it, and then it's expelled, so that your final product is the acetone, the monosubstituted acetone with the R group here. Here's a methyl group here. Here's the methyl group here. Here's the carbon, the carbonyl, the carbon and the carbonyl bonded double bond to the oxygen. So here again, you can do this and add 2 R groups as opposed to 1. The idea is we're going to do the same thing like you did, except after you get to this step, you're just simply going to deprotonate another hydrogen bonded right here, but you're sandwiched between the 2 carbonyl groups, and it's going to produce a negative charge right here, and you just add another alkyl halide, which by doing so you remove the halogen portion of it, and you add the R group to it solely, and then you just follow the same steps. So you protonate the ethyl ester, the ethyl oxygen, the portion, and then you heat it so that you have decarboxylation, so you remove the carboxylic acid. And so yeah, that's it.